Now let's derive the formula that we had in our previous video for the vector triple product. And what we need to consider here is adjusting and orienting our coordinate frame, our coordinate axes, such that vector b lies directly on the x-axis. Okay, and the reason we do that is just to simplify our derivation. Okay, so we need to consider our vector b such that it lies directly on the x-axis. Okay, and to make it general, we will consider vector c and a to be anywhere in our coordinate frame. And it's important to remember that the way we adjust our coordinate frame should not impact our result. Okay, so just because we choose our coordinate axes such that b lies on x should not affect our result. Now I've drawn out the other coordinate axes, and it's important to remember that we chose our coordinate frame such that the vector b lies directly on the x-axis over here. Okay? Now let's write down the expressions for vector b, c, and a. So since vector b lies directly on the x-axis, it will only have a component in the I hat direction. And I hat is essentially the unit vector associated with the x-axis. Okay, so I've drawn out the unit vectors associated with each axis. So now we can write down the expressions for the other vectors. So the vector c will have components in the xy plane. So we'll have one component in the I hat direction and another component in the j hat direction. Okay, and similarly for a, it will have component in the I, j, and k hat direction. Now we can calculate our vector triple product. But first, what we need to do is compute the first part of the vector triple product, which is in parentheses. In other words, b cross c. And the way we do that is by using the determinant form for the cross product. Okay, so here we have I, j, and k. And so b only has a component in the I hat direction. So we have bx over here, but 0 and 0 over there. And c has components in the I and j hat direction. And geometrically, we can visualize the cross product by noting that the resulting vector will only be in the k hat direction. Okay, so computing this, we have a component in the k hat direction, and its component will be bx cy. Note that we multiply bx by cy, and 0 times cx. 0 times cx equals 0. So we only consider bx times cy. Good. Now we can compute the rest of the vector triple product by once again using our determinant form. And noting that here we have the cross product essentially between two vectors, because b cross c is one vector, which is given over here, and we have our second vector a. All right, so I've written down the components for each vector, and remember that for cross products the order matters. So first you need to write down the components of a in the determinant, and then write down the components of b cross c. Good. Now what you need to do is cross multiply for each component. Ultimately, this gives us ay times bx cy in the I hat direction minus ax bx, cy in the j hat direction. Now let's go over what we have just obtained here. So in the previous video, I said that the vector triple product ultimately gives us a vector that will lie in the plane spanned by the vectors b and c. And this is exactly what we get here. We get a vector that has components in the I hat and j hat direction. And in this particular case, the xy plane corresponds to the planes spanned by the vectors b and c. So this form that we get essentially makes sense. However, it is important to remember that what we want to get is a linear combination of the vectors b and c, right? So what we need to have is a scalar multiplied by vector b plus another scalar that multiplies vector c. Okay, and this is the form we want to obtain. And so what we need to do for the rest of this video is manipulate this expression so that at the end we obtain this expression over here. Firstly, to visualize this a bit better, we will write this vector in component form. So we have lambda 1 bxi plus lambda 2. Note that we have vector c that has components in the I and j hat direction. So what we have is lambda 2 times cx in the I hat direction plus lambda 2 in the j hat direction. Good. Now we notice here that we are on the right path of deriving our formula, because here we have bx that multiplies the I hat unit vector, and here we have a similar expression, except we have ay and cy. However, we also need a cx component for the I hat direction, but in our expression over here we do not have cx. Okay, and for j hat we're also on the right path because we have a cy component, which is similar to this expression. Now what we need to do is change this expression, and the way we do that is we will add and subtract a vector, and the vector that we add and subtract will be ax, bx, cx in the I hat direction. Remember, the only thing we need to change is in the I hat direction, because for j hat we already have a good expression here, because we need cy j hat, and that's what we have. So we add and multiply the vector that I wrote in blue here, and so what we get is ay bx cy plus ax bx cx in the I hat direction minus ax bx cy. Of course, we can't forget to subtract this vector since we added it at the beginning. So we have minus ax bx cx, all of that in the I hat direction. Good. Now notice here that we can factorize by bx over here, which is exactly what we want, because remember that our final formula needs to be in this form. Alright? Good. So by factorizing we obtain bx ay cy plus ax cx in the I hat direction. And similarly here what we can do is factorize by ax bx. And so we have cyj plus cxi. We are in the final steps of our derivation, And what we notice here is that this expression is actually the expression for the dot product of A and C. So this is A dot C, okay, which is a scalar. And similarly, AX BX is the dot product of A and B. And therefore, there we have it. We have finished our derivation. Let me rewrite down the whole expression again. Now, what we need to recognize is that bxi is essentially our vector b, and similarly, cyj plus cxi is essentially our vector c over here. And so, what we ultimately get is a dotted with c times vector b minus a dotted with b times vector c. And this is the expression for the vector triple product. And what we need to note is that this expression is a lot simpler than when we had to do cross products, because dot products are a lot easier to compute relative to cross products. Okay, and so thank you for watching this video. I hope you liked it. Leave a comment down below, of course, if you have any questions.